In section 3B, the overall theme that we're going to be looking at is scientific notation. Okay, so what is scientific notation? Simply put, it is a way to take numbers that have a lot of digits. You want to be careful not to discuss them as very large numbers because that's not really what it is. But it's to take a number that has a lot of digits, something that's very lengthy, and to sort of like compress the size and how you need to write it to make it look smaller so that you don't have to write all the digits that would be in the number. The top part up here with the introduction, I'm not going to really read through that. You can see what the answers are, and if you want to, you can check your work there and just see how you feel about those answers. What I'm going to do is go straight to the box here, which talks about what scientific notation actually does with the numbers. All right, so you have two different cases, and that's all there are. There's two cases here where you can have lots of digits and numbers. This might be the one that you normally would think of here. This is a very, very large number. Like its quantity, what its value is worth is very large. Each of these sets of numbers here where you have the commas, these are called periods. So you've got 1, 2, 3, 4 periods, and then you're moving into what we call a fifth period. So a very large number. This is the thousands area, this is the millions area, this is the billions, and then we're way out here in the trillions. So it's an incredibly large number that we see here. And if you had to do a calculation with this, or if you just had to type it up, it has a lot of digits to go on there. And there's value to seeing them. There definitely is value to seeing the number of like periods that you have and to realize that this is such a large number. But at some point, it might become a little bit tedious to write all that out. So what we do is we take the numbers that are towards the beginning. In this case, this example, they used all the digits that are there that are not zeros, but you can do a little bit of rounding. That's actually a normal thing that we'll do to save even more kind of like space when you're writing. But you take the numbers that are towards the beginning and you put a decimal point right after the first digit. So we'll see that here. We're going to have the 1.7345. Okay, so we move a decimal into that spot. Now, if you just put a decimal in that spot and then drop off all these zeros at the end of it, ending with that number, obviously you've changed what it's worth because that would only be 1.7, where this was 17 trillion. But to adjust for the fact that we've moved the decimal all the way up to that spot, what we're going to do is multiply by a lot of tens. Because recall that every time you multiply by 10, just in general, you take any number and you multiply it by 10, that decimal point is going to move back a spot, right? As an example, if I just took 72 and multiply that by 10, I get 720. Okay, so if I took 8.6 and multiply that by 100, what that's going to do, so this essentially 100 is times 10 times 10, it's two tens. That's going to move the decimal place back to 86 for the first 10 and then move it to 860 for the next 10. So if we're multiplying by just a lot of tens, that decimal point is going to move back every time you multiply by 10. So we place the decimal here after the 1, and if we multiply by 10 13 times, what that's going to do is move the decimal point back 1, 2, 3, 4. Okay, that's 4, but we'd still need to move another 9 times to get all the way to the end of it, and that's where all these zeros come in. Okay, that'd be another 3, 6, and then 9. Okay, so this is a different way to write the number, just in a more compressed size than what you have here. And the direction that we're going to be going with this is showing you that if you have to do calculations with numbers that look like this, it's probably going to be easier just to write them up in that form. All right, the other one is what we would have as a very, very small number. Okay, so this is way less than 1. This is the real number here. It's way less than 1. You've got a lot of zeros in there, and then you've got 175. All right, rule is basically the same thing here. What you want to do is take the actual number spots, so sort of skip over all the extra zeros, move on to the number area, and then put a decimal right after the first digit. So we get 1.75. Okay. But when you multiply by 10 this time, you don't, well, what you're going to see here is the exponent is you're going to have a negative one, because a negative exponent, because if you have a positive exponent, that's going to cause the decimal to move backwards. So if we use a negative exponent, what it does is moves it to the left. It moves it back to the front, making it a smaller number. As a little side note here, this is true. We're not going to get into a lot of depth on why this part works. That's not part of our class, but if you have a negative exponent, so you're multiplying by 10 to the negative 15, that negative exponent actually means to divide. That's what negative exponents are, and I guess I'll say that bit of information now is that negative exponents don't actually mean negative. What they mean is to divide. So instead of multiplying 1.75 by 10 15 times, you're actually going to divide it by 10 15 times, which is going to move that decimal to the front. The hard thing that you're going to see here, I think, with these is you don't have all those little commas that are in between, so you got to be very careful that you're literally counting all the zeros, and you might want to do them a couple times. These are easier, right? You got 3, 6, 9, 12, 13. But here you're going to have to count a little bit more. All right, so questions 3 and 4, numbers that are large will end up having positive exponents because what we're doing is we're stealing some of those places there, some of those digits, right? And to give them back, you need to multiply by the 10. Okay, and then when you see the smaller numbers, those are going to have the negative powers because when you move the decimal over, you actually made it larger. So using a negative power is going to bring it back down to the correct size. So same things that were just talked about there. Question 4, we're going to do just a little bit of practice. What you're going to see here is the top one's already worked out for you, which is pretty cool. So you get to see that one in its complete form. The next, all you're going to do is talk about the 10 to the power, and then the last one, you're going to do the entire number that would be there. Okay, so just to talk about this one, I'm glad that they did this here because I briefly mentioned before that you don't have to take all of the digits like up here. You don't actually have to take all 5 digits plus that are not zeros. Plus, if you have other numbers that aren't zeros, you don't want to be like in the mindset that you have to keep every number that's not a zero. You can round things off. You could actually call this 1.7 times 10 to the 13th power, which is sort of what they did here, right? They have the 175, but they went ahead and just changed it to 1.8. It does change the value of the number, that's true, but sometimes rounding is still a thing that we want to do in the problems. I don't know if it actually said to do any rounding here. I don't know. All right, so what they did is they moved the decimal point right here. The 5 then ended up rounding up to 7, 2, and 8. So now we just we count spots, right? You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 zeros, and then you have one more to get that decimal place behind the 1, which is going to give you your 15. And of course, because it's one of the smaller numbers, remember just use a negative exponent. That's generally the rule. Remember that small numbers are negatives, large numbers will be the positives. All right, so the next decimal place is going to go right there. So let's count all the zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus an extra is going to give you 11. So it's going to be 2.2 times 10 to 11. Just double count those. Okay, so I got that wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, it's kind of hard to do with the camera above it as well, so I think I got them right. If I miscounted, obviously you could fix what I did. All right, calcium, let's see here. We're going to write the number part first here that we'd end up with. So your decimal place is going to end up right after the 5. So you could either do 5.96. This is kind of an interesting one here because you can do 5.96, or if you want to round it off, it gets a little bit odd, right? Because that 6 is actually going to kick up that 9. Okay, so if that moves the 9 up, it actually becomes a 10, which causes that to be a 6. So your choices will be 5.96, or you can do 6.0. Sometimes there's rounding ones where one rounding rolls into a 9 and then that rolls over into the next number. It can get a little bit tough. Now, if you are going to round that up, if you're going to round this up so that causes this to turn to ultimately 6, you should keep the 0. Okay, we do want to keep that. Don't just drop that off. I always think there's an importance to not rounding things to whole values without showing that extra 0. because at least that 0 tells us that it wasn't a perfect 6, or gives us the idea that it might not have been. Okay, so I'll put that one in there, but if you're more comfortable with this one, that's totally fine. All right, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, plus an extra will be 10. Yeah. Again, if I miscounted that, it's just because the camera's in my face here, so hopefully I did get them right. All right, this is also part of question 4 here. What we're doing is the other end of this, which would be the big numbers. And you know what? To keep this super authentic here, and you probably caught this earlier, I realize now, because these are the larger numbers, if I go back to this part, these are bad answers, aren't they? And I'm gonna pause there just in case you didn't catch that bit. These are bad answers because if we have little numbers, these should be negative exponents, okay? So we got to be careful about this stuff. It's actually going to be 10 to the negative 11th. This is going to be 10 to the negative 10th. Over here is where you're going to get the positive exponents for all of these. All right, so Germany, I think these are a little bit easier because you got all the little periods that you count on these. Oh, above here, we do get to see it rounded off. That's the number we saw from the very beginning. So they did round it off at just 1.7. All right, for this, we're gonna do 5.7. Yep, they've already done that one for us. And then we got 3, 6, 9, 12. 10 to the 12, so that's an easier one because you can count by the 3's here. All right, for this one, you could just call it 3. That's fine, you can call it 3.0 if you want to, because this one actually is a solid number at, I think that might be 3 trillion. We got millions, billion, trillion. At 3 trillion, you could just leave it at 3. You don't need the 0 for that one. And you do get 3, 6, 9, 12 again. So 12 power for that. All right, question 5. We're just working backwards on things, right? So we took all the real numbers that have all those extra zeros and the lot of digits in them and changed them into scientific notation. This is taking the scientific notation and changing it into the actual numbers. All right, so if you have a positive exponent, that means that your decimal place is going to go to the right. I'll fix that little arrow there. It's going to go to the right. When you have the negative exponents, that decimal place is going to go to the left. All right, so we got 1.2. You're going to move the decimal place over 6 spots. Now, one of those spots is going to happen when it moves right behind the 2. So that'll count as your first one. And then you could say, well, if I've already done one move to get it behind the 2, so it looks like at 12, that means that I need 5 more zeros added onto the end of it. So just add the 5 zeros, then throw in some commas where they would fit, and that's that. All right, so this one is going to move to the left 3 spots. So one spot's going to get you in front of the 6, which means that you need to move forward 2 more times. So you're going to have 2 zeros, then your 6, 9. So you had to move forward in front of the 6. That's 1, 2, and 3 goes there. And then what's a good idea is to put another 0 in the front. One of the benefits of having that 0 in the front is sometimes our decimal points aren't as obvious as we want them to be, and for some reason, even if you do write a decimal somewhat small, by having that 0 in the front, maybe the spacing of it, it sort of highlights that there is a decimal sitting in that spot. So it's just a helpful thing to do. Question 6, 7, 8, and 9 are going to use scientific notation in sort of a neat way here that I always thought. The background on this, before I talk about any of them, is in a lot of articles that you might read or things that you might see in the news, they'll say stuff like 32 billion. They'll throw something out like that, right? They'll just say 32 billion, and we get an idea what that means because we know our place values that billions they're bigger than millions, but they're not as large as trillions. So we get a concept of what they are. And it's a nice way to write things also, just to see it printed somewhere. Like here's this, right? 2.2 million. Like you've seen things written like this a lot. However, once you get to the point that you need to do calculations with them, what you would need to do is convert it into a real number, right? If you're going to do a calculation with 2.2 million, you're going to want to look at it as 2, comma 200,000. You want to look at it that way. But what this offers you here is this alternative that, well, maybe you don't really need to add on all the zeros if you just multiply it by 10 with the appropriate number. Okay, so let's go back up at the top here. Anytime you see something that says blank thousand, well, 1,000 itself is worth 10 to the third power, 10 times 10 times 10. So if you're told some value 1,000, you could actually just write in scientific notation, letting this be that times 10 to the power portion. For a million, that would be 10 6 times. For a billion, that'd be 10 9 times, and then a trillion is 10 12 times. And you should see that these count by threes, right? You got 3, 6, 9, 12, because each of those moves you into a different period of things. So we go thousands to millions to billions to trillions. We don't do anything with 100,000s. Those aren't really in these things. These are actually the main checkpoints for the periods. Okay, so 2.2 million, so 2.2 million looks like this. It's 2, comma 200,000. So I said that a moment ago, but I think it helps to actually see it. That is 2.2 million. Okay, but you can express it in this form. You could leave it like this, because if your ultimate goal is to do some calculations with it, you might choose just to leave it in that form until you get to the end, and then you can decide how you want to state your final answers. All right, next we got 2,608 billion. Okay, so that's the same thing as 2,608 times 10 to the 9th, because billions are going to be nines. You do want to get used to these numbers. You'll use them a few times throughout the course here. All right, now follow up to what we just wrote here. Let me write it all in print, just because I think when some of it's typed and some of it's not, it's a little bit odd. Okay, so 7 says, is that scientific notation? Technically, the answer is no, it's not scientific notation, because the decimal place should be right after the 2. That's where it should be. Okay, that's where your decimal place should end up being. So no, it is not. Explain, you should only have one number that's in front of the decimal. Does it, make it wrong on a test if we want you to convert something in scientific notation? Yes, we want to have that decimal in that front spot. But is it still a usable number to work things out? And the answer to that would be yes. It's still usable, and it's definitely going to be a lot less to write than, this. See what it looks like. So I have to have 9 zeros on the end. Okay, so it may be easier to work with than that number, even though it's not technically in scientific notation. Okay, now number 8 says, let's go ahead and change it into scientific notation though. Okay, let's convert it over. So you can see, I didn't put the exponent there because I wanted to talk about that part. Okay, we're going to move that decimal place right here. Okay, and when we do that, when we move the decimal spot from here to there, we are essentially stealing 3 place values that we have here. We're taking away 3 values. We're making 2,608 look smaller, which means to balance it, we have to add the extra place values in this exponent over here. So we used to have a 9, but now we're going to gain 1, 2, 3 more. So that's going to move it up to a 12. So that's what it would look like in scientific notation, which also changes the way that you could read this value here. You can now actually call it 2.6 trillion. You could call it that one. They're not always going to add or land on a new, type of number like this, a new period, but that one happens too because it moves 3 decimal spots over. All right, question number 9. What we're going to do is look at one calculation with scientific notation involved in it. Unfortunately, the question starts on page 2 and then finishes up on the next. Okay, but it says here that in 2000, the U.S. health expenditures were about 1.4 trillion, and 2016, the amount increased to 3.3 trillion. Okay, we want to write each of these numbers in scientific notation. Okay, so we'll go to the next page here. All right, these are those numbers in scientific notation. That's the 1.4, and since it was trillion, that's going to be 10 to the 12th. 3.3 trillion is going to be 3.3 and then 10 to the 12th. So these are both in the trillions. They both have the same thing there. And B is going to give us a little bit of a throwback to what we did in 3A, section 3A, that we just recently talked about. Find the percent increase in healthcare spending. Okay, and here's a little box to remind you what all that stuff is. And remember, I called it the new minus old divided by old. So if something is like chronological in a way here, you can think of it as time. What was the newest value? What was the older value? So the setup here said that in 2000, we had the 1.4. In 2016, we had the 3.3. So this would be the new value. That would be the old value. Okay, so everything's set up. Here's your new value, 3.3 times 10 to the 12th, and then you get your old value, 1.4 times 10 to the 12th, and then that ends up on the bottom as well. And that was the importance of knowing new versus old, because whatever is in that spot is the same thing that's going to be on the bottom. Okay, this ends up being a really unique case with the scientific notation, because if you look at all three terms that we have, here, here, and here, if you look at all of them, they have the exact same scientific notation. So what you're allowed to do is divide that number out of all of them. In other words, these all just drop out of the problem. That's going to be a little bit tricky to explain why it works, and I think I'll try and do a little sample problem with something else here in just a moment. But here's one rule to start with. If every single number that is in your problem involving division has that same scientific notation, yes, you can remove it. You can remove that. Okay, so then it just becomes this, and there's no trillions anymore. The trillions are all divided out. So we're just going to do 3.3 minus 1.4, which will give us 1.9. Divide that by 1.4, you get 1.357, which what I'll go ahead and do is keep 2 decimal places here. Okay, so that ends up being we'll say 3, wanted around and then I missed it there. 3.6, which is the same thing as if you want to change it into a percentage form, if you want to change it into a percentage, that will be 136%. So that was actually a really good idea. I kept 2 decimals. Kind of thought that far ahead of it, but it played out pretty good. Okay, this whole division thing here. Let me see if I can think of an example that I'd want. Dividing by 2s is pretty nice, so I'll choose some numbers like that. Let's say I have 6 minus, let's do a larger number, 6 minus 8 divided by, it doesn't have to be the same number for what I'm trying to show here, but let's see if I can actually create one that will work well. Let's do a 4. Try and predict numbers that work. Okay, so the idea what I'm showing up here is that if everything is divisible by the same number, then you can divide that out at the beginning. In our case, it was the scientific notation, so we divided it all from there. All of these numbers happen to be divisible by, I was trying to go for 2, but they're also all divisible by 4. So if I want to, I can divide every single number by 4, which will give me 16 divided by 4 is 4, 8 divided by 4 is 2, and then 4 divided by 4 is 1. And that will simplify down to 2 over 1, which is 2. Okay? Now, if we don't totally buy into that that's true, that you can divide every one of these by the same number and it results in the right answer, let's look at doing our normal order of operations. And if we subtract these two things, we get 8 over 4, right? 16 minus 8 is going to be 8 over 4, and 8 divided by 4, in fact, is 2. Okay, where this might get tricky with the scientific notation is if these aren't exactly the same. Okay, so I'm not going to touch on that in the notes here, but if you do have one of these that might be different, like maybe this one was actually 10 to the 9th power, something like that. I guess this would be 10 to the 9th as well. But if you had a couple that were 10 to the ninth and one that's 10 to the 12th, the trick would be to force them to all have the same 10 to a power. So make an adjustment somewhere so that you can cancel out all the scientific notation. That may show up in something else that we'll get to look at later on, and if it does, then we'll address it at that spot. For the second part of 3B, we're going to do more calculations involving scientific notation. At the end of the last part, what we did was a single problem that used percent increase. What we're going to do in this one is go back to stuff that we did in 2A, which was unit conversions. But we're going to be doing these in terms of scientific notation. Okay, for the top part here, questions 1 and 2, those are just to kind of get your feet wet with what we're going to be doing for the next couple pages here, which is all the unit conversions stuff. So I'm not going to really read like what I wrote for these, but you can take a look at my answers and think about what you did. But the point is that the first part, you're supposed to think about, wow, these numbers are kind of hard to imagine what their sizes would be and how much they're worth. And then the second part is to get you to look at this reference table that's been provided for you. All right, up at the top here, we've got 3B. The other stuff that's on this page, you're not going to need these. We're not going to use them at all, so don't really worry about them. It's just this top part up here. Okay, and what this table tells us is the amount of energy that would be used for different things. All right, so the energy released by the metabolism of one candy bar will be 1 times 10 to the 6 joules. So it's a scientific notation number. And then you've got the energy needed for an hour running, which would be 4 times 10 to the 6 power. Remember that these right here are, these are the millions place values. So that'd be 1 million, that's 4 million. The 7s, you can't quite call numbers like that, but you get down to the 9. That one was billion, so this is 1.6 billion joules is what we get from burning 1 kilogram of coal. Anyhow, you have a list of a bunch of things there, and you should probably read over them just to familiarize yourself with what stuff is on there. Okay, so question number 3. What they want us to do is figure out how many days of energy that 1 kilogram of coal could provide for an average home. I think that's the same question they ask up at the top, but now we get to work it out. Okay, so unit conversion. You can see here that we have all the fractions. We also call this dimensional analysis, if you remember that. Okay, what you have is a series of fractions that are going to multiply and then result in the answer that we want. So what we're starting with is going to be the 1 kilogram of coal. That's the beginning part. And then we're going to think about how much energy that we get from that kilogram of coal. We're then going to think about how much energy that we need for an average home, like daily, and then that will ultimately tell us how many days of energy that we get from that. Okay, so here's where we start with 1 kilogram coal. And you go ahead and place that over 1. If it were a per type situation, you could go ahead and put it over whatever would go on the bottom. But I believe most of these questions are just going to start with, like, you've got a kilogram of coal, so just put it over 1. Okay, so 1 kilogram coal here. We're going to convert that into its energy form. So from the table, you'll be told that 1 kilogram of coal is worth 1.6 times 10 to the 9th joules. Where did that table go? Probably just keep it loose here. All right, so 1 kilogram of coal, right there, and there's the 1.6 times 10 to the 9th. So we're going to take that number and set up a fraction out of this because they're equivalent to each other. Okay, so the coal is on the bottom because we want that to cancel out with the coals that we have here. And we have essentially converted the kilogram of coal into how much energy it is, which is this number. Okay, now what we want to do is convert that energy into the number of days that we can get for a house. Okay, so next we look up the average daily, like the average use in a home is going to be 5 times 10 to the 7th joules. Okay, and since we had joules on top, we're going to do the 5 times 10 to the 7 joules on the bottom. That is going to be worth 1 day of energy for the house. Okay, so now the joules are going to cancel out, which is going to leave us with days, and that's what we're trying to find here. So that'll conclude the setup. The rest of it is now to do the math. So I've already took out the units. Across the top, the ones aren't really going to do anything, so you're keeping the 1.6 times 10 to the ninth. For the bottom, same thing, you're not going to use those ones. You're going to have 5 times 10 to the seventh. All right, ultimately, this is what the answer turns out to be. It's 32 days. And I think it might be exactly 32. Okay, yeah. All right, turns out to be exactly 32 days. Now, over to the side here, I went ahead and wrote down a little bit more information because it isn't so obvious that it just jumps into that answer. Okay, so here's what you want to do. Well, you actually have two choices. This is the choice I'm going to send you in the direction of, though. I'll explain that one first. Go ahead and just divide these two numbers. And that's what I did. I divided the 1.6 by the 5, and I get 0.32. That's first step. Second, divide the scientific notation, which that can be done using the quotient rule that we looked at previously. I forget which section that one is, but dividing these two things, you can actually just subtract their exponents, which is going to give you 2. Okay, 9 minus 7 will give you 2. So ultimately, this is the answer that I'm looking at. It's from the division of those numbers, the 0.32, and then the quotient rule dividing these two, you get 10 to the second power. Now from here, what I'm going to do is adjust the number. First, if I want to change it just into true scientific notation, it would end up being 3.2, so you only get 1 decimal spot. So I would move it back, okay? I'd move it back. It's like I'm giving it an extra place value by making it larger, so I need to steal a number from that exponent, and it would be times 10 to the first power. Okay, so that would be the answer in true scientific notation form. However, if we think about what this number means, the better answer is actually called 32, because it means 3.2 times 10 one time, which would just move the decimal spot back one more, which would get you through 32 days. Okay, so it's a little bit odd, all the things that are happening, but it's important that we understand what we want from an answer. It does, it just, there's something weird about saying 3.2 times 10 to the first power days. That just means 32 days. That's all it is. All right, now your other alternative approach, though not really encouraged because some of these problems will get long, you could take these numbers and just change them into real values, right? So move the decimal over one spot for the 6, and then I need 8 more. And divide that by 5 with 7 zeros. 6, 7. And you get 32. So you do that. But if you have a lot of these types of numbers in the problem, it might not be the best approach. And it's always good to try out things that might be a little bit different than what we've normally done. All right, question 4. One hand, it's a cool question because it's kind of funny when you read it. Mathematically, it's not that great of a problem because you're going to end up noticing that the scientific notation on the top and the bottom are the same, so they just eliminate each other as you go through it. Okay, more importantly though, let's talk about the setup. Where is our question? How many candy bars do you need to eat for 1 hour of running? Obviously, you shouldn't be eating candy bars for energy, but that's not totally the point. All right, what are we going to start with? We're going to start with what we want to accomplish. We want to accomplish 1 hour of running. So that's where we begin. What we want to convert 1 hour running into is the number of candy bars needed. Okay, so sometimes, so it's flipped in the order of the sentence, right? So you want to be careful about like, what is it that we're trying to get? What is that we're trying to accomplish? And that might actually be the beginning of the problem. All right, so these are values just taken from the table. I'll let you look at that if you want, but it does, 1 candy bar is going to be equal to 1 times 10 to the 6 joules, where 1 hour running is 4 times 10 to the 6 powers joules. Again, just check that out on the table if you want. All right, so we start with our running, and we're going to place that over 1, which I had mentioned that I believe most of the problems here, if not all of them, are just going to start with an over 1 situation. Okay, so that you don't dive straight into this part here. Just let that be the top, and then it'll work itself out. All right, so we're going to convert that into the amount of energy needed. So we're going to put that 1 hour on the bottom so that it will cancel with the 1 hour that's on the top. It is equivalent to 4 times 10 to the 6 power joules that's on top. Next, what we're going to do is convert that amount of joules into candy bars. So now we're going to use this conversion, placing the joules on the bottom so that they will cancel. 1 times 10 to the 6 power joules is 1 candy bar. Okay, so now we've converted into candy bars, and that would be the unit that we want at the end. If that completes all of this, it's a matter of now putting it together. So all the extra like ones, not that one, that one, that one, that one, that one, those don't really do anything, right? Because you're just timesing by 1. So you're really only going to be taking this number and dividing it by that number. So we see it here. And as I mentioned just a little bit ago, because these both have the same scientific notation, it's almost not as interesting of a problem. They'll just cancel out. I guess that's interesting in their own, but these do just cancel out, which will give you 4 divided by 1, which is 4. As a follow-up question, using your answer from number 4, how many candy bars do you need to eat for 3 hours of running? Well, if that's worth 1, just multiply it by 3 and you get 12. Question 6 and 7 are going to be a little bit more practice on this dimensional analysis with the scientific notation. A little bit more practice is obviously going to be good so you can get the hang of what's going on here. Question 6, how many kilograms of uranium would be required to supply the energy needs for the U.S. for 1 year using fission? Notice that it does have these 2 things in bold print. So they're trying to help you out by picking out the things that we need here. The goal here is, for the problem, the goal here is to supply the U.S. for 1 year of energy. So that's actually going to be your starting value, even though that's what we're trying to get to. What we want to do is to think about how much energy is needed for 1 year and then convert that into how many kilograms of uranium would be equivalent to that. Okay, so here's the actual problem. But above here, there's a couple of the things that you would need to get from the table that's on the other page. 1 year of energy for the U.S. is going to be 1 times 10 to the 20th power. Be careful about a few of these, like you do have U.S. annual energy consumption, you have world annual energy consumption, and then there's also like the daily home one. So make sure that you're paying attention to which of those they actually are. Okay, so here's the U.S. for 1 year. And 1 kilogram of uranium is going to be worth that amount. Okay, yes. So those will be conversions that will show up as fractions in a little bit here. All right, we begin with 1 year because that's what we want the energy for 1 year. We're then going to convert 1 year into joules. Okay, so the years will cancel out, which will leave you with the amount of energy that we needed from 1 year. Next, we're going to convert that energy into kilograms of uranium by taking that comparison and placing joules on the bottom. Joules will cancel out and we end up with the number of kilograms of uranium. So yeah, these are the only units that are left over, kilograms of uranium, so that gets us to our endpoint. That one, and that one don't really do anything when you multiply, so we're really looking at this number divided by that number, which you can see I've placed over here. All right, so now you've got these 2 choices in how you evaluate this final part. You could type in 1 with 20 zeros on the end of it, and divide it by a 56 with another 12 zeros on the end of that one, and it'll give you an answer. Or you can do it in the parts, which is what I'm encouraging you to do in this activity. Like start with the 1 divided by the 5.6. So 2 parts we're doing. Okay, I'll take 1 divided by 5.6, which will give me that number. I'll ultimately end up rounding it because you're not going to want to take every single decimal point that you have in here, or digit, I should say it that way. How did I write? Okay, so I wrote it down in its true form here with the decimal front. So we are going to move it in a moment so it looks like real scientific notation, but I did round off to 3 places. Okay, then the 10 to the powers, this part's always really easy. You just take the exponent that you have on the top and you subtract the exponent that's on the bottom. So 20 minus 13 is 7. So this is the answer in those 2 parts. Dividing the true numbers, I get 0.179. Subtracting the exponents in the scientific notation, I get the 7. Okay, now since that's not a true scientific notation, what I'm going to do is adjust it just a little bit. What I'm going to do is move the decimal place back one spot so I get 1.79. But when I do that, I've made the number appear larger than it is. I've multiplied it by 10 to go from here to there. So if I multiplied it by 10 to change this part, I need to get that 10 from somewhere. So I'm going to take it away from the scientific power part of this whole thing and drop that down to a 6. And conveniently for the problem, 10 to the 6 is actually million, right? We saw that in the other part. So you could really now restate the answer as it would require 1.79 million kilograms of uranium. Now that was a bit of conveniency that decimal place, when you move it, puts it into the forms of a million, but you could, have this option to maybe move a decimal a couple times if moving it twice would get it into a good spot, like millions or billions for that. All right, so 7. If you could generate energy by fusing hydrogen, how much water in liters is required to supply the energy consumption worldwide for 1 year? Okay, so we want to use hydrogen to supply energy consumption for the world for a year. So we're actually going to begin with this part here. That's what we want to have. That's the only concrete number that we know. We're trying to convert that into the hydrogen. So looking this up on the table, worldwide for 1 year is going to be the 5.3 times 10 to the 20 power. Okay, 5.3 times 10 to the 20 power. Okay, so I'm going to start with 1 year, then convert that into energy. So years will cancel, and I got the number that I just showed you there. All right, next I'm going to convert that energy into hydrogen. Okay, so I'm going to go look that up. Where are you? Right there. Okay, released from fission hydrogen, 1 liter of water, 6.9 times 10 to the 13. Okay, so 6.9 times 10 to the 13 is going to be on the bottom with the joules so that they cancel. The top is going to be 1 liter of hydrogen. Okay, so that's all kind of included together there, 1 liter of hydrogen, which is what we want to get to. So that's all the dimensional analysis. We'll take what we actually have on the top, which is this number, what we have on the bottom, and we're going to divide those two. Okay, doing it in parts, I will divide the 5.3 by 6.9, which is going to give us 0.768 right there, and then subtracting these numbers, you're going to get 10 to the 7th power. Okay, now that not being in true scientific notation, it's basically the same thing you saw in the last problem. We're going to move that back one spot, so we get 7.68. But if you move it back, you need to take away one of the 10s that we've got on the back end, so times 10 to the 6. So this one also turns out to be a nice kind of number you could write as 7.68 million. You could write it that way. All right, for our last problem here, what we're going to do is compare two quantities that happen to be in scientific notation. We did this previously in something else. You should recognize this, that if you want to compare two quantities, you take the larger one and you divide it by the smaller one. Okay, that's how we do that. In scientific notation, really all that means is you should use the method that I've been doing up here, where we just divide the two numbers and then we do quotient rule of subtracting, and that becomes your comparison. Okay, so if we want to compare a liter of oil, the energy for a liter of oil to the energy of a candy bar, we'd want to first go to that table and look up these numbers. For a liter of oil, it's going to be 1.2 times 10 to the 7th power, where a candy bar is 1 times 10 to the 6th. Okay, now that exponent is the main reason why this one's bigger than that one. Okay, it's definitely times 10 larger with that. All right, so your larger one is going to be the oil. There's that number. Here's your smaller one. To do a comparison of these values, what we want you to do is divide the larger number by the smaller one. So I'll divide 1.2 by 1, which gives me 1.2. Dividing the 10 to the 7th by 10 to the 6th, you're actually going to be subtracting these two, which will give you 10 to the first power. Now, this one, whenever you have 10 to the first power, it's a little bit of an odd thing. I don't really think you should ever write times 10 to the first power. What you should do is just go to whatever number you have and just move the decimal back one spot. Go ahead and multiply the 1.2 by that 10, which just becomes a nice number of 12. Okay. Usually you want to keep the scientific notation numbers if it's something like in the millions or larger. Even if it's like times 10 to the 2, I would just go ahead and move that back 2 spots and call it 120, something like that. So that's my ideas on that and what I'd suggest. Okay, and then what we want to be able to do is write sentences like this. This is the actual comparison here. Okay, we start with our bigger quality. We would say that quantity. We'd start with 1 liter of oil releases 12 times as much energy that's released by 1 candy bar. So it's always the bigger one, whatever we got from the division, times our smaller quantity.